We're going to, in this video, we're going to work through section 20.4, which starts on page 922. We're going to be looking at free energy change and equilibrium. So this is kind of wrapping everything together that we've been talking about this last couple of months in terms of looking at how equilibrium processes work and kind of the direction a reaction will go, as well as the free energy that we've just learned about, is how that's connected to the two, because those two topics are connected and related to each other. So we're just going to start with this relation looking at delta G. So delta G is the Gibbs energy, and when it's negative, a reaction is spontaneous we should typically say spontaneous in the forward direction. We're usually talking about the forward direction for a reaction just by convention. And we would say that's when we're looking at a reaction, the difference in energy or the free energy available for that reaction is going to be the kind of what we call the initial starting conditions, or our reaction quotient Q, looking at how much energy is available there. So that's just multiplied by RT, which is our proportionality constant. And we look at the difference from how far away it is from K. So we're kind of looking at the difference between these two is going to be how much energy is available for this reaction to either release or absorb. So it could be that if Q is greater than K, then delta G will be positive, and the reaction is going to release some energy and go the opposite direction. Or it could be that Q is less than K, and the reaction will have some free energy available to absorb to make this process go forward. It's kind of weird the way I've said it, but the textbook will kind of clarify that as well. We choose the conditions for Q in this case to be standard conditions. And we'll see why in just a second here. So remember, standard conditions means we have 1 atmosphere of pressure if we're dealing with gases, or a 1 molar aqueous solution, or if we're dealing with a pure liquid or solid, then we just assume it's the pure liquid or solid, and those don't worry about the equilibrium as well. They don't show up in Q or K. So under these standard conditions of 1 atmosphere and 1 molar, Q is equal to 1, and so the RT ln Q term becomes 0. And since we're now under standard conditions, we get to put a little not symbol on the delta G. So we're saying the standard free energy change for any process is simply negative RT ln K, because the whole Q term just goes away. So RT ln Q, the natural log of 1 is 0, so RT0 is 0. So we end up with this really important formula, delta G is equal to negative RT ln K. And it's important, and I've even put this into work that I have published. So some of my published articles from graduate school simply use this formula, and I cited my general chemistry textbook, just because it's that fundamental, and it works even in more advanced research settings where we were kind of predicting, using a program to predict delta G values. And from this formula, with the standard delta G, we could calculate what the equilibrium concentrations would be, and I could compare that to my experiment and see if I was getting close. So this is a very powerful and important equation. What we can do with this now, so this is under standard conditions. We chose Q to be 1 molar, and more often than not, as we saw in lab, Q was not always 1 molar. In fact, it was usually not 1 molar. So there's other times when Q will not be equal to standard conditions, and so now we need to kind of think about how can we modify this in order to make sure we can calculate the Gibbs energy under non-standard conditions. And so what we do is we go back to our equations. We say delta G is equal to RT ln Q minus RT ln K. And we're going to say that now we're going to be under non-standard conditions, so we'll be looking at Q again, but this time we're not going to set it as 1 molar. We're just going to let it be whatever it'll be. And I work through a practice problem at the end of this video to kind of illustrate this whole thing. So what we'll do is we're going to take this equation that we just used above, delta G naught is equal to negative RT ln K, and we're going to plug that in for the negative RT ln K. And we're going to flip the negative sign around as well. So what we end up with is that delta G under any conditions, and I apologize, my G's start to look like 6s when I draw too quickly. Delta G under any conditions will be delta G naught plus RT ln Q. And again, this is another really powerful equation because what we have here is the standard free energy change and then we have Q over here if we're not at standard conditions, so this will modify delta G naught. This whole term RT ln Q modifies delta G naught for non-standard conditions. So we're calculating delta G when we're not at standard conditions. So we can kind of conclude just for this little section here. So if, just looking back at this equation, and let me put a quick box around it because it is kind of important. So looking at this, we can see if Q is less than K, we already know from our basic understanding of equilibria earlier, if Q is less than K, then the reaction is going to proceed to right. And we're kind of proven that because the delta G for that, under those conditions, doesn't matter what Q is, as long as it's less than K, the delta G will be less than 0, and the reaction is spontaneous in the forward direction. So we kind of, again, we said that if Q is less than K, then the reaction will go towards products, and the delta G is backing that up. Or it's kind of proving that there is free energy available for the forward reaction. If Q is greater than K, then looking back at that equation we just wrote up, then delta G will be greater than 0, and we'd say the reaction is non-spontaneous in the forward directions. And finally, if Q is equal to K, then all of this drops out, and delta G simply becomes 0. And so this is always for the forward reactions. And remember, when Q is equal to K, we're at equilibrium, and when we set it, we're at equilibrium, delta G is equal to 0. Both the forward and reverse reactions are happening spontaneously. So let's do a quick practice problem with this. This is example 20.11 in the textbook, and that's on page 926. Part A is saying, well, we need to calculate K at, this is going to be confusing, 298 K. So we're calculating the equilibrium constant K at 298 K, given a standard delta G naught at 298 is equal to negative 141.6 kilojoules per mole. Again, Gibbs energy is typically given in kilojoules per mole because it's a large value. And then for part B, we're given some conditions. We have 0.5 atmospheres of SO2, and I guess I should have written the reaction, so I skipped a step here. We're doing the oxidation of SO2, oxidizing it to produce SO3, which is a precursor for making sulfuric acid. Okay, so we have 0.5 atmospheres of SO2, 0.0100 atmospheres of O2, and 0.100 atmospheres of the SO3. And this is at 25 C, so 298 Kelvin. And we want to figure out which direction the reaction is going to go. And finally, in part C, we're going to calculate the delta G for the conditions in part B. So we'll just jump right in for part A. I'm given a delta G naught, and I want to figure out what K is. So we'll start off with one of the first reactions we put in the box today. Delta G naught is equal to negative RT ln K. and we just need to solve for K, so we're going to rearrange this a little bit. And the first thing I'm going to do is divide both sides by negative RT. So now I have delta G naught divided by negative RT is equal to ln K. And to get rid of that natural log, and actually let's move this negative sign up. Doesn't matter, it's all negative. To get rid of the natural log, we raise both sides to the e. So we can end up finally with, I'm going to kind of rewrite this really quickly. We end up with K is equal to e to the negative delta G naught over RT. So just plugging some of these values in, we have K is equal to E, and I of course did not give myself enough room. Let's move that down. This is going to be negative, and give yourself plenty of room here, negative 141.6 kilojoules per mole. But we're going to have to change from kilojoules into joules because our gas constant R is in joules, so we're going to multiply this by 1,000 joules per kilojoule. And so that'll cancel out kilojoules. And this all gets divided by RT. So R is 8.314 joules per mole Kelvin, and T is 298 Kelvin. So our Kelvin terms cancel out, and we'll just have joules per mole over joules per mole. K will end up being unitless as it should be. And so K, once we crunch all the numbers, it's equal to e to the 57.2, which again, K is simply equal to 7 times 10 to the 24th. So that's part A. Let's do a quick critical thinking check here and make sure our answer makes sense. The standard Gibbs energy for this reaction, delta G naught, is a very large negative number. So negative 141.6 kilojoules per mole. That's a lot of negative free energy. And what that means when delta G naught is negative, that means it's spontaneous. So this is a lot of energy free for the reaction to go forward. So this reaction is going to go forward spontaneously. And we calculate K, which is saying that this reaction, if we just looked at K by itself, we would say, wow, K is a very large number. This reaction favors the product, so it should be going towards the products. So those two are kind of agreeing with each other that with a large negative delta G naught and a large equilibrium constant K, these should both agree and say that the reaction is going to favor products. So that's our critical thinking check. Part B asked us, under a different set of conditions, which direction is the reaction going to go. So we need to calculate Q, and we can write Q, remember, is always just the ratio of products over reactants. So in this case, it's going to be the pressure of the SO3 squared over the pressure of the SO2 squared times the pressure of O2. So this becomes Q is equal to 0.100 squared divided by 0.500 squared times 0.0, ooh, that was terrible, 0.00100, and that's just by itself. Crunch those numbers, Q is just 4. Handwriting is atrocious today. Q is 4, so we're done there. Which direction is the reaction going to go? We always have to compare Q versus K, and we just calculated K right up there, and Q, 4, is much less than 7 times 10 to the 24th, so Q is less than K. This reaction is going to go to the right. It's going to favor products. So we say the reaction goes towards products. And again, just a quick critical thinking check. We kind of knew that should be happening because the Gibbs free energy was very negative. So under these new conditions, we have very little of the product around. We only have 0.1 atmosphere of product and a lot of reactant around. So this reaction wants to favor products, and there's really not much product around. It's still mostly reactants. So it's going to proceed to the right to produce some of those products, and that's what that negative Gibbs energy is telling us as well. So let's calculate the Gibbs energy under these conditions just to kind of make sure that that's giving us the value we expect. So under these new conditions, we're going to figure out what the non-standard Gibbs energy is, and that's compared to the standard Gibbs energy plus our new condition. So that's the RT, ln, Q. So delta G, non-standard Gibbs energy, is just going to be standard Gibbs energy negative 141.6 kilojoules per mole. And I'm going to change that into joules again really quickly. And this gets added to RT, ln, Q, so R is 8.314 joules, so there's why I changed it to joules. Joules per mole Kelvin times 298 Kelvin. Those were the conditions. Well, it told us 25 degrees Celsius, but that's 298 Kelvin. And then natural log of Q, which in the previous problem, Q was just 4.00. So we can just plug all those in together. What we end up with is negative 1.41.6. Oh, can't do that. 1.416 times 10 to the 5th joules per mole plus 3.43 times 10 to the 3rd joules per mole. And this is delta G. So for our final answer, delta G ends up being negative 1.382 times 10 to the 3rd joules, or we could rewrite that in kilojoules. That's negative 138.2 kilojoules per mole. And again, just one more quick critical thinking check. We know that under the conditions given above, that this reaction is going to favor products, and Q was a very small number, so this reaction still wasn't favoring products. And we calculated under these new conditions with that Q that we still get a very large negative delta G value. So this reaction still has a lot of free energy to go towards products, and so this reaction would proceed to the right to produce more products, kind of like we calculated in part B, until delta G is equal to 0 and we've reached equilibrium where Q is equal to K. So we're kind of using that negative 138.2 kilojoules in order to drive this reaction forward until delta G is equal to 0. We've used all that energy up. And just a quick point to mention, the reverse reaction, so if we were to come the other way, then that's 1 over Q, and delta G becomes a positive number. So the reverse reaction is non-spontaneous. It will not happen. So there's our quick critical thinking check. And that's all for this video.